So today I'll be talking about nucleophilic substitution involving haloalkanes. So I'll first talk about haloalkanes. So these molecules are polar, and it's because there's a difference in electron negativity between the carbon and the halogen. And actually the halogen holds on to the electrons a lot more compared to the carbon, which makes it slightly negative, and then thus the carbon slightly positive and electron deficient. So this is important because the other part of our reaction is the nucleophiles. And nucleophiles has a lot of electrons, and they are willing to give away these electrons, and thus they are attracted to the electron deficient carbon. There are two different nucleophilic substitution that can occur, and it depends on the type of haloalkane. If the haloalkane has 3 alkyl groups attached to the carbon where the halogen is attached to, this is a tertiary haloalkane. And then the other haloalkane we need to know is a primary alkane. And a primary alkane is when the carbon that has the halogen is only attached to one alkyl group. So something like that. Okay, so I'll start off talking about the mechanism for the tertiary haloalkane. And it is the central carbon atom that is electron deficient. Our nucleophile is going to be a hydroxide ion. So at this moment, the hydroxide is unable to go to the central carbon that is attracted to, because we just have too much going on. We have a halogen and 3 alkyl groups. So there is some steric hindrance. So before the reaction occurs, we actually have to break the bond between the carbon and the chlorine. So what happens is that both of the electrons in their bond goes to the chlorine atom. And this step actually has a very high activation energy needed for this to occur. So it is also the rate determining step. So then what we have is the central carbon atom is a lot more free for the nucleophile to go to. However, to have a better understanding of how the nucleophile gives its electron to the carbon atom, we need to go back to hybridization to understand the orbitals of the central carbon. So in central carbon, we have 3 electron domains, so it would be, I'll just put a yellow there. We have an sp2 hybridization, and we have only 3 electrons currently in the carbon atom, because remember, one was taken from the chlorine. So when we hybridize 3 orbitals, we have this, we actually have 1 unhybridized p orbital. Hydroxide ions can either lend its orbitals to the top of the p orbital or the bottom of the p orbital, and this has like a 50-50 chance of occurring. So there are names for a nucleophilic substitution reaction. They're actually noted with the letters SN, so like substitution of nucleophiles, I guess. And if you go back to the rate determining step, there's only one molecule involved in the rate determining step. The type of reaction is known as SN1. And to draw the final molecule, it could look something, I mean, it's 50-50, so anything could happen, but I'll just draw it down here. And yeah, then the nucleophile takes the place of the halogen, hence the name nucleophilic substitution. Now I'll be talking about the mechanism for primary haloalkane. So it is the middle carbon, like the last one, that is electron deficient. However, there's less alkyl groups around the central carbon, which means that the hydroxide ion is able to immediately react with it and lend its electrons to the carbon. This is also the rate determining step of this reaction, so this step has a very high activation energy. And what I'm going to draw here next is something that only occurs theoretically, and is something that scientists calls a transition state, because this, if it does like happen, it is happens for like milliseconds. So this is a transition state because, as you can tell, looks weird as carbon doesn't have 5 electrons to give. But what happens in this transition state is that as the hydroxide ions is giving its electrons to the electron deficient carbon, this becomes like very negative over here. So the electrons in the bond between the carbon and chlorine actually gets repulsed, and then the electrons from this bond goes to the chlorine. Kind of something similar that happened with the previous reaction. So what we have in the end is this, that we have the bond, the OH, and then plus the chloride ion. And I think something that's very important to note here is because there's so much electrons in the hydroxide ions, it has a very strong repulsive force. So you can see the alkyl group was originally here, but then at the end of the reaction, it kind of gets pushed away from this hydroxide ion to the other side of this molecule. As for naming this type of nucleophilic substitution, we will name it after the rate determining step. And in the rate determining step, we actually have 2 molecules this time, the hydroxide ion and the haloalkane. So since we have 2, we name this reaction with SN2. So here are some factors affecting the rate of reaction. So the first one, you want a higher electron density for a faster rate. This means like having more lone pairs of electrons, and it could also be a smaller atomic orbital, because this means the electrons are more concentrated, but mainly it's the first one. The other one is you want a greater difference in electronegativity between the carbon and the halogen. So the halogen has to be a lot more electronegative. This means fluorine reacts faster than bromine, which reacts faster than chlorine. This is because if the halogen is a lot more electronegative, it is a lot easier for it to get the electron of the carbon, so then the bond is a lot weaker and easier to break. The last one is the type of haloalkane. So tertiary will react the fastest because it is more inclined to go to the SN1 route, and the rate determining step, which is the fission of the halogen to carbon bond, has a lower activation energy compared to SN2's rate determining step, which is the transition state. I haven't talked about the secondary haloalkane, and it's because it can either go to the S1 or the SN2 route, or a little bit of both, so it's a lot more complicated. So yeah, thank you for listening.